Now we're going to talk about some periodic trends. And these are trends, they are not hard and fast rules, right? And we deal with trends like this in everyday life. If I asked you to predict who was larger, a fifth grader or a third grader, what would you tell me? The fifth grader is probably larger. Is that always true? No. But generally, right? So generally that's useful, right? We can make generalizations about males and females. There are exceptions, right? And there's exceptions to everything. So what we're looking at here with the periodic trends are generalizations. They can be very helpful, which is why we talk about them at all, but they're not hard and fast rules. And we're not going to be learning the details and the exceptions. We're going to be learning the general rules. So the first one we're going to look at is atomic size. And before we look at the trend in atomic size, we have to decide, well, how are we going to define that? Because we've learned that the atom is a nucleus with a bunch of electrons in these kind of standing waves, but yet they're particles. And so how do you say where the edge of that is, right? There are lots of different ways to define the radius of an atom. One way is called the van der Waals radius, or the non-bonding atomic radius. And so that's taking half the distance between adjacent nuclei in the atomic solid. So here's krypton as a solid. You can make it a solid at a really, really low temperature. And we can measure the distance between these two nuclei. We can't do much with the electrons themselves, but we can measure the distance between the two nuclei and say, well, if the centers of the atoms are this much apart, then the radius of the atom must be half of that. So we could do that. We can also look at a bonding atomic radius or a covalent radius. So we could look at two bromine atoms that are bonded together in a bromine molecule. And again, we can measure the distance between the nuclei and say, well, the radius is half of that. But when these two atoms bond together, their nuclei get closer. They kind of overlap with each other, and so they squish in. And so that bonding radius is always going to be smaller than the non-bonding radius. So there's some other ways we can measure it too. I tell you about those just to let you know that measuring the radius of an atom is not necessarily a simple process. We're just going to call atomic radius an average radius based on measuring the radius in lots of different forms, as an element, as a compound, and so we sort of generally average them. So that number is a kind of a soft number. It's not exact. It's very definitely an average, an estimate. We can approximate a bond length. So like in that bromine molecule, what's the length of the bond? Well, we could say that's the sum of the atomic radii. That's going to be an approximate length of that bond. That works for covalent bonds. It doesn't work for ionic bonds. So what are the trends in the atomic radius? The atomic radius increases as you go down a group in the periodic table. This trend makes a lot of sense. If we look at the noble gases, we've got helium has a mass of 4, and neon is 20, and argon is 40. Or we can look at the number of electrons, 2, 10, 18, 36. As we're going down, we're gaining mass and we're gaining number of electrons, and so it makes sense that the lower ones must be larger, right? And that's true. Yay, there's a trend that makes sense. On this graph, which looks like all over the place, right? We're looking at atomic radius, that's in picometers, as a function of atomic number, just so we can spread all the elements out. Here's helium, neon, argon, krypton, xenon, and we see there is a trend here that as we go down that group, the elements get larger. Is it linear? No. Do we care about that right now? No, we don't. It's just we can predict that xenon is going to have a larger radius than krypton. We can also look at the alkali metals, group 1. Here's lithium, sodium, potassium, rubidium, cesium. And again, as we go down, the radius gets larger. Now, the difference between rubidium and cesium is pretty small. You might not predict that, but we're just looking at the general trend. Any questions about that? Now let's go back to this one and talk about it. So let's look at the trend as you go across a period. So lithium is in period 2 of the periodic table, and then next is beryllium and boron and carbon and nitrogen and oxygen and fluorine and neon. And so here we see there's a definite drop. Initially here it's going down, and then here, there's some little irregularities, but in general, it's decreasing as we go across. That does not intuitively make sense. Neon weighs more than lithium. Neon has more electrons than lithium. This doesn't make much sense. And yet we see this trend for all of the periods. As we go across from left to right, the atoms get smaller. So what is up with that? Here we can see a periodic table where the height of the little squares is relative to its atomic radius, and the radii are given here. And so we can look at lithium 152, beryllium 112, and they're just sinking. So that's the one we still need to explain. This trend, they're getting bigger as we go down, and that works for all of the groups. We're going to ignore the transition metals for now. That one makes sense. So why do they get smaller? Well, this gets back to shielding. So when we have a multi-electron system, which is everything but hydrogen, we've got the attraction with the nucleus and repulsion from the other electrons. The outer electrons, the ones that are farthest away, they're going to have a bigger impact on measuring the size of the atom because they're the outermost ones. They are shielded from the nucleus by the core electrons, and we talked about this in chapter 8. So this shielding causes the outer electrons to not experience the full strength of the nuclear charge. Here's a picture. I like to use lithium for this because it's relatively simple. So here's, there are 3 protons in the nucleus, and here we have our 1s2, the 1s subshell. We've got 2 electrons in there. Those are the core electrons. Let's just write the electron configuration is 1s2, 2s1. So these are the core electrons, and this is the valence electron. So here's our valence electron out here. When the valence electron is looking at the nucleus, these electrons are sort of obscuring its view. They're kind of repelling it. I talked about people on the beach. Yesterday, I came up with a better analogy. Actually, it was kind of a group effort. So the nucleus is a celebrity, okay? And the electrons are just like regular people, and they're attracted to the celebrity. They want to get close, see them, get their autograph or something. So these electrons are the ones that got really close to the celebrity. And this valence electron is looking at the celebrity, and it's got this crowd of people around it, and so he can't really see the celebrity very well. And if you go out farther and farther in the crowd, the guy's way out on the edge. They can just maybe get a glimpse of that person every once in a while. Does that make sense? And we're not talking about penetration here, but when we did talk about penetration, those are the orbitals where the electrons you could think of as being especially pushy, and they're just going to push their way through the crowd to get closer. We liked it yesterday. Anyway, so here, this electron, because there's this crowd of people around the nucleus, these two electrons sort of negate part of this charge. So we can say the effective nuclear charge is the positive 3 that's there, but then there's 2 core electrons that are in the way, and so we subtract that from the positive charge, and that valence electron sees an effective charge of +1. Does that make sense? So the effective nuclear charge, it's given the symbol ZEFF for effective. It's Z, which is the atomic number of protons, minus S, and S is the charge shielded by the core electrons. So essentially, the number of core electrons. Well, hydrogen and helium do not have any shielding because they don't have any core electrons versus valence electrons. But all the other elements do experience some shielding because the core electrons are closer and they shield the nucleus from the valence electrons. We're going to look at that difference in just a minute. So this is a very simplistic approximation of the effective nuclear charge, but it's good enough for our purposes. So let's look at what are the effective nuclear charges of nitrogen and of argon. So what we have to do here is look at how many core electrons, how many valence electrons. So it could be helpful to look at the electron configuration. So for nitrogen, what's the electron configuration? Very good. 1s2, 2s2, 2p3. And if you need some help with that, review Monday's lecture. Okay, so which of those are the valence electrons? The 2s, right? These are the valence electrons. And so then these are the core electrons. So core electrons, valence electrons. So the effective nuclear charge is the atomic number. What's the atomic number for nitrogen? 7. There are 7 protons, and then we're going to subtract the number of core electrons. How many core electrons? 2. So the effective nuclear charge here is 5. Because there's an inner core of 2 electrons, there's this small crowd around the nucleus that's shielding it from the rest of the electrons. So let's look at argon. What's the electron configuration for argon? Yeah, 1s2, 2s2, 2p6. Oh wait, we're not done. I was thinking neon. 3s2, 3p6. Which are the valence electrons? The ones in the 3rd level. So there's, these are the valence electrons, and everything else, those are the core electrons. How many core electrons are there? 2 plus 2 plus 6 is 10, right? So there's 10 of those. So looking at effective nuclear charge for argon, argon has an atomic number of 18. And then we're going to subtract the number of core electrons, and that gives us an 8. Argon has a larger effective nuclear charge than nitrogen does. Any questions? If we looked at, say, chlorine, let's just look at that for a minute. So chlorine, 1s2, 2s2, 2p6, 3s2, 3p5, right? Here are the valence electrons, and if we're looking at, there's our valence electrons and our core electrons. How many core electrons does chlorine have? 10. But if we do the effective nuclear charge for chlorine, how many protons are in the nucleus? 17. And then we subtract the valence electrons. And so the effective nuclear charge for chlorine is 7. The core electrons are the same, but what's different is the nucleus, right? Yes? It tends to correspond to the group number, yeah. Mm-hmm. Okay, so here we have the quantum mechanical explanation for that trend in atomic radius. As we're moving down a column, we're thinking, well, we don't really need an explanation here, but you're going to get one anyway. As you're going down a column, the principal quantum number of the valence electrons is increasing. You're going from n equals 1, n equals 2, n equals 3. Those orbitals are, on average, farther and farther. They're larger, so they're average farther away from the nucleus. So that makes the element larger, right? When we're going across a period, I just showed you with chlorine and argon, and Alex observed the effective nuclear charge, which we are approximating, is approximately the same as the group number. We see that the effective nuclear charge increases. Those electrons are in the same principal level. So let's see, I'll go back to this one. So for chlorine, the valence electrons are on the third principal level, the third floor of the hotel. For argon, they're also on the third floor. So the distance, just based on principal energy level, is roughly the same, but the effective nuclear charge is larger for argon. And so this gets into Coulomb's law. We've got a stronger attraction, and so we end up with a smaller radius. So we learned that the potential energy of attraction between two charged particles is Q1 times Q2 over R. How to draw this? So I'm pretending that this is chlorine, and we're just looking at the effective nuclear charge on those valence electrons. So these valence electrons are seeing a plus 7, and they have a -1 charge. For argon, here's there's a +8 effective nuclear charge. I'm trying to make that, it's roughly the same size. And the electron out here is -1, and it's being attracted to the nucleus. They're in the third level. Here it's more convenient to think of the Bohr model, where n equals 3 is this orbit in a specific distance from the nucleus. Right, so all other things being equal, the distance would be the same. So R here would be the same. And so what we can look at that's different is Q1 and Q2. Here, Q1 is 7, and Q2 is -1. Here, Q1 is 8, and this is -1. The attraction of the nucleus for these valence electrons is larger for argon. And so they are more attracted, they're going to pull in. And so that's why argon is actually a little smaller than chlorine. One more time. Just trying to think if I can come up with a different way to say it. I don't know. So chlorine and argon have their valence electrons in the same levels, right? Roughly the same distance from the nucleus. But because of the difference in number of protons in the nucleus, the charge on the nucleus is different. And so these valence electrons experience a +7 charge, and these experience a +8 charge. These electrons are more attracted because the charges are larger.
So the overall level is just
So that'll pull them in a little bit. So you've got maybe a so-so star, it's got some appeal, and people are crowded around, but, we're not going to push way in because, not that awesome. And then you've got somebody who's like a superstar, I don't know, Robert Downey Jr. A thing for Robert Downey Jr. And the people around him are going to push in closer because he's more attractive to them. Does that make sense? Yeah, so here Q1, where to write this? Q1 equals +7, and Q2 equals -1. For argon, Q1 equals +8, and Q2 equals -1. Q2 is the electron, the charge on the electron, which is always -1. So we're looking at the attraction of the nucleus for each valence electron separately, not overall together, because they are individuals. So here, Q1 times Q2 is -7. Here it's -8. The larger the negative number, the stronger the attraction. And then because this is larger and the electrons can move, they can be pulled in tighter, what's going to happen is they're going to get squeezed in a little bit, and so then the radius is going to go down, and that's just going to be even stronger attraction. What about those transition metals? Well, we still see a trend going down the column because we're adding electrons into larger and larger levels. But when we go across a period, the atomic radii of the transition metals are roughly the same. There's not a strong trend like there is with the main group elements. The reason for this is, what's the valence shell for the transition elements? It's NS2. Whatever the period number is, S. It's not the D. And so when we're adding electrons in there, we are adding core electrons, not valence electrons, and so the effective nuclear charge is approximately the same for all of them. Yeah, because those, I need a periodic table. Well, yeah. Well, I guess we could use this one. Use this periodic table. That's what I meant to do. It's only Wednesday. Okay. So, I gotta write on this. This would be 1, 2, 3, 4, 5 periods. So these are the 4 s electrons, and here we imagine adding in 3d electrons. So chromium has more 3d electrons than scandium. Copper has more 3d electrons than vanadium. But all of those are core electrons. So we add a core electron going from manganese to iron. We're also adding a proton. So the actual charge goes up by 1. But because the number of core electrons goes up by 1, the effective nuclear charge stays the same. Okay? And so we see as we look at the numbers here, 162, 147, 134, you're like, well, it's going down, but then it kind of goes up and down and up and down. And so what we want you to remember is it's like kind of the same. It's just the same, and we'll call it good. Okay? So on the basis of periodic trends, choose the larger atom in each pair, if possible. So we have to find these on a periodic table, and I meant to stick a periodic table in that big empty spot, and I forgot. So I will draw a little tiny piece of the periodic table. So we've got tin or iodine. So those are in the same row, the same period. There's tin, and then there's antimony and tellurium, and iodine's over here. So then we kind of talk to ourselves, and we say, well, what's the trend? When I go down a group, it gets bigger. That makes sense. When I go across, it was all that stuff about shielding and things, and what I remember is it's not what I expect. It gets smaller. I thought it should get bigger, but it gets smaller. So going across, iodine is smaller than tin, right? So it says choose the larger one. Tin's larger. Okay? Germanium or polonium. You don't actually need to know their names. You just have to be able to find the letters on the periodic table. Here's germanium, and here's polonium down at an angle. I'm like, oh, I don't know about this. So there are two trends. The trend going across is that they're getting smaller. Polonium is to the right. So we would predict that polonium is smaller based on that one. So going across predicts that germanium is larger. But the trend going down says that the elements get larger as we go down, and that trend predicts that polonium's larger. We got opposing trends. This is the if possible. So for a question like this that was open-ended, I would accept two answers. I would accept it's not possible because the trends are opposite and I'm not sure which one is more important. So I can't tell. Perfectly valid answer. If you were forced to choose, if I was forced to choose, I would say that this vertical trend is stronger than the effective nuclear charge trend going across, and I would predict polonium. But for you, I would expect you to say, not possible, you can't tell. Okay? How about CR or W, chromium or tungsten? So again, I'm going to find a little piece of the periodic table with those, bless you. So here's chromium, and tungsten is down there. Which one's bigger? Tungsten. Because it's lower on the periodic table. You go down a group, they get bigger. You go across a period left to right like we read, and they get smaller. Yes?
Which one did you say was stronger, going across or down?
Going down. Because when you're going down, you're actually adding a new layer, right? When you're going across, you're just looking at a little bit of an increase in the charges. So in general, I would say that the vertical trend is stronger. Any other questions? That's a question that could very well be on the exam. A question just like that with different elements, of course.